Hello everyone, my name is Tom Jose. I am working as a lead research and development engineer at Mirabilis Design. I'll be your host for today's webinar titled Accelerated Development in Automotive Electric and Electronic Systems using VisualSim Architect. Before we go into the webinar, a little bit of logistics. All the attendees participating in this webinar will be placed on mute. In order to ask a question, click on the cloud chat sign and type in the questions in the chat window. We'll be answering them once the session gets over, or if there is a limited time, then we'll be responding to them via email. So the agenda for today's session comprises of these following topics. We'll be first looking at the trends and challenges in a typical automotive E systems, the key automotive E system technologies, which covers the hardware, networking, and the software aspects. Then we introduce you to system modeling, where we assemble the entire automotive electric and electronic systems. Then we go through some of the examples and use cases where we look at each of the different aspects and the impact they have on modeling the system. And last, we will go through the history of Mirabilis design and an overview of what VisualSim Architect is capable of. So what are the challenges that an architect normally faces in the development of an EE system for auto? So typically, since the automotive system is a huge system which comprises of hardware, software, networking, and power domains, it is often very difficult to find a single platform where we can develop all the components together. So most of the times, the network engineers use a tool aid for their exploration. Then the hardware engineers use another set of tools and sources online to conduct their researches. But then there is not a single platform where they can combine all of these studies together and test them under a single platform. And then there are other challenges like how to link it all together, then how to scale it up. So in often cases, the laboratory test suite is only limited to a limited number of nodes. For example, the lab setup might only have one or two nodes, a single switch, and then even that might take a large number of resources to be put in to get it to work. Then there is a fine tuning, and which is all an overhead added tool. So it is very difficult to scale the number of nodes or ECUs in the test setup in the laboratory to be operating at hundreds or 500s or thousands of nodes. Now, another challenge comes in where we have to link all of our results and studies with the exploration and link it with the results. So there we'll be running a lot of result test cases, and we need to identify which of them satisfies our requirements and create a separate list of them, so that we can at the end we can determine which configuration or which setup we have to go through. And then we also have to conduct various trade-off studies. For example, the power versus performance. There might be a limited power that is available for a particular task, but then with that much amount of power, how much can be the maximum performance that we can obtain out of it? So then there comes the safety, reliability, the quantity of cost, and quality of service. All of those needs to be considered as well. So this is where we comes in with the VisualSim Automotive E system development platform. In today's session, we will use the VisualSim Architect and see how it can be used to model the complete automotive electric and electronic system, which would include the hardware modeling, the software design, and the network configurations. And each of these models that we create, we'll be looking at how we can evaluate the performance side of it, the power side of it, and the functionality side of it. So once we have developed this system, then we can evaluate the corresponding system's behavior for different faults. So let's say we developed the system and we evaluated it, it all works fine. But we also need to know how the system is going to perform under different faults. So we'll look at hardware failure, software failure, RTOS failure, power failure, and network failure in detail. So in order to give you an overview, so for example, let's take a look at this model constructed in VisualSim Architect. So this is our modeling environment where the user can assemble the components in a graphical interface. Each of the components that we see over here can be obtained from the library over here on the left hand side. So if you go into here, interface and buses, we can go into each of the specific folders and select the component that we want to use in the target model. So let's say if I want to add another TSN switch, I can simply drag and drop into the modeling environment. Then it will be placed into the platform as required. Then we can also have different nodes. Then the traffic generators. The traffic generators are also very important when modeling such a system. So we can see like, the TSN switches here. Then for gateways, similarly, we can add gateways here, CAN FDs, various networking protocols. All of these can be easily dragged and dropped into the modeling platform as we require. So there is no development that is required from the user side. They can simply reuse these verified and validated IPs. And as per requirement, we can simply update these parameters as entered here. So some of the key VisualSim technologies that the user could leverage of are seen from the libraries in the previous example. We have wide range of networking protocols like the CAN FD, the flux race, the audio-video bridging, the time-sensitive networking, time-triggered Ethernet, gigabit Ethernet, the AFDX, 5G, 6G library support, and a limited vehicle-to-vehicle demo models as well. So that is on the networking protocol side. Then on the hardware and software, the user has access to various gateway demo models, various configuration switches, including the NXPs, TSN enabled switches, then multiple varieties of processor cores, the ARM cores, the RISC-V cores, then various schedulers, including round robin, weighted round robin, strict priority, credit-based shapers, arbitraries, queues, and so on. And from the software side, the user can define how the task should flow. A task graph definition is possible with the tool, and then the software code execution. Let's say we want to run the C code or CPP code onto the tool. That is also possible. And then the hardware software partitioning can also be done using this environment. Then another important side of it is the integration of various components. For example, on a big system like this, there will be a huge number of sensors. So we have to model the traffic generation capabilities. It can either be read from a CSV file or an ARXML file, maybe directly from the Wireshark, or maybe from the lab environment itself. Then we also integrate cybersecurity, failure models, error generation, and also support multi-core simulation. So this makes the simulation run a lot faster as we distribute it across multiple cores. So it is essentially an all-in-one package for network, hardware, software analysis, verification, and testing. So now the question comes, why study the bandwidth allocations and timing deadline? So just as a small example is shown here, let's say we have 3 different packets flowing at different time intervals. Each has a different traffic profile associated with it. Now, some of them will be having a higher priority and some of them will be having low priority. So depending upon the time of arrival and the priority assigned to it, the behavior that we will be getting out of the system will be different. So it is very important that we analyze all of these traffic settings or time configurations beforehand so that we can make sure that the high priority packets arrive at the destination within the strict time deadlines. Now, let's look at the importance of selecting the right architecture. So for example, from the architect's point of view, there's a variety of communication templates available. There is a variety of processing units and templates available. Then a variety of scheduling or arbitration algorithms also are available. So it is very important that we select the right architecture suiting for application. So it can be either be an architecture number 1 kind of an approach, or be a splitted, distributed kind of an processing approach, where each of the units are distributed across an interconnect mechanism, and the path can be statically defined. So according to the applications that we want to run on top of it, the architecture that we select will be having a huge importance. So it is very important that we select the correct architecture suited for our application much early in the design process itself. So now going ahead, the architecture exploration methodology is being explained here. So we start off with the product requirements. It can be that the number of sensors that is required for a system, the power consumption requirements, or the safety or security requirements. And then we can also define the architecture requirements, like how many number of ECUs are there, the bus or the topology requirements. And then we assemble them all together in our environment, and then we run different simulations on it. And the results from those simulations are then taken in and are used to optimize and then run again. So this becomes a closed loop approach. So all of these requirements are linked with our architecture exploration using our AI enhanced diagnostic block. So user can enter in the requirements using a database or a table like a CSV file, and then the diagnostic block will run through the simulations in the backend and give us recommendations and the results, whether the requirements are being met or not. This becomes very valuable for the architect in the sense that they gain insights onto how to optimize the parameters and get desired results. So some of the system model experiments include the different gate control lists for the time hour shaper to meet timing deadlines, because this is what is responsible for opening and closing of the gates in the time hour shaper. Then using experiments to determine which is better for our application, like a credit-based shaper versus a strict priority scheduling. So this is in order to meet the bandwidth requirements for the class A and B frames of AVPs. Then we can do scalability test, where we can scale the number of nodes from 2 to 6 to 500s of nodes. Then the performance with and without redundancy. So when we add the redundancy into the system, then a set of resources will be dedicated in case the previous set of resources undergo some failure or faulty. So that affects the performance, but the safety can be guaranteed there. Then we also experiment with software mapping sequences, where we experiment with sequential execution versus parallel execution versus cascade execution. Some of the common evaluation statistics are the response times for safety critical tasks, the throughput across multi-hierarchical bus networks, the packet drop rate across buffers and networks, because we should make sure that critical packets are not being buffered too much across the links. The memory usage, because there is a limited memory available and we should always limit the off-chip DRAM accesses. The CPU utilizations, the power consumption over a period of time, we will monitor the peak and average power consumed per device. The battery discharge rate, with and without data encryption, so as to know which is better approach over time. Then the credit analysis with frozen and non-frozen credit during the guard band period. So now we'll be looking at some of the use case examples. We'll be going through network modeling, where we look at the network side of automotive system, EE system, where we specifically look at the quality of service settings, the routing algorithms, the topology approach, and so on. Under software modeling methodology, we'll be looking at the software definition and mapping of tasks in automotive EE system. It includes task cascading, task graph definition, execution of software code. Under hardware modeling side, we'll be looking at the hardware architecture of an EE system. It will include the ECU design, resource management, cache analysis, interconnect accesses, and so on. And lastly, under failure analysis, we will injecting faults at various levels within the automotive system. It will be injected in hardware side, the software aspect, the power, RTOS, and the networking aspect. So we'll be starting off with the network modeling use cases. So the very first use case that we have selected is related to the very promising time-sensitive networking standard case studies, which include credit-based shaper versus strict priority. So our agenda for this use case was to evaluate the performance gain, especially for the throughput and the packet spacing when we are using a credit-based shaper enabled switch versus a strict priority scheduler enabled switch, because most of the existing switches mostly uses strict priority, but the upcoming or the latest gen switches are moved over to to support TSN standards. So we need to evaluate this in order to identify whether we need to invest in the newer uh, protocols and technologies. So for evaluating this test case, we have two traffic generators used. One is a class B traffic sent via port A at an average rate of 90 Mbps, and another traffic generator which is generating best effort traffic at an average rate of 60 Mbps. So they are both being sent to the same destination port, and we are using for the grid-based shaper. We have to input the ideal slope and sense slope values for the classes A and B, so as to allocate the bandwidth required for classes A and B. For the strict priority scheduler, it will simply look at the priority of the frames and select the highest priority packet. So this is the environmental setup. We have the class ABB packet generated by a traffic generator, the best effort frames generated by another traffic generator. They are all going into the switch via a different port, and they all go to the same destination where we have connected a sync to determine the stats. So the very first use case is using the credit-based shaper, and we reserve 55 megabits per second for the ABB class. So this is the parameter settings that we have used. The reservation value is 55 Mbps. So we use this equation to calculate the ideal slope and set slope. And the corresponding value was entered into the parameter window of the switch in VisualSim Architect simulation platform. So once we run the simulation, we could see the following graph. We could see the ingress throughput at around the average throughput around 80 to 90 Mbps, and this is just for the TSN or the ABB packet. And at the output side, we could see that the ABB has a dedicated 55 megabits per second, and the remaining 45 megabits per second were used by the best effort frames, because that was only what was available for the best effort frames to be used. And the egress packet spacing looks considerably better because for the ingress side, we could see there is a lot of spikes, but for the egress side, it is moderated. And for the second use case, we are looking at the strict priority scheduler and without any credit-based shape. So this is the parameter settings that we have used. The resource controller is set to scheduler and not TSN controller. And the scheduler option is set to strict priority. We can see the various options that we have in this window. Round robin, first come first serve, weighted round robin, deficit round robin, then round robin priority, and so on and so on. So user can evaluate different scheduling algorithms just by changing these parameter options, this pull down option. So these are the results that we got, and we could see that since we are using a strict priority scheduler, the best effort frame, which is a priority 7 frame, is given the highest priority here. So the best effort frame uses 60 megabits per second, while only 40 megabits per second was given to the ABB frame. So here the better performance is being presented by the best effort frames. So we could clearly see what are the benefits and impacts when using a grid-based shaper versus a strict scheduler. Now we look at a complex multi-layer network model. We could see that we have a linear best topology versus a star topology model over on the right. So it is very easy to connect them up by just updating the settings in the routing table. We can easily evaluate various topologies. Over here in this model, we are evaluating or exploring different protocols to meet the quality of service. So by evaluating, let's say, whether it is a bandwidth limited or latency constrained valuation model, we are able to determine the right protocol that should be used to meet the quality of service. Now, we'll be looking at the software modeling use cases. So we could see here that in this model, we have the task graph defined at the bottom. So we can see the function 1 triggers both function 2 and 3. And for the function 4 to get started, it requires the completion of both function 2 and 3. So there is a dependency in the software execution, and all of these tasks are mapped to the hardware architecture or the network topology shown on top. So in a single model, we are able to evaluate the software definition, the hardware architecture, as well as the network topology. So these were some of the statistics that are generated from the simulation. We could see the latency for each of the functions separately and the latency for the complete function. So we could see for each of the application, what is the performance that we could get out of it. And for each of the tweaks we make, what are the gains that we can get out of it. All of these information can be easily understood from the model. So now we are going to look at some of the hardware modeling use cases. So here we have a subsystem, or for a system evaluation, we can use a system like this. So here we have the top level model where we have CAN networks, each of the sensors connected to each of the nodes. Then we have the break ECU. And within this break ECU, we can see the processor or the ECU system being set up, the memory system, the bus networks, all of these being set up in the same model. So once and all of these are set up using the library components available on the left-hand side. So this from the simulation, we were able to get information on the power, the amount of heat dissipated, and the functional and timing analysis reports. So using this, we could see here that the functional messages, for example, whether the correct data has been read, whether incorrect data has been read, these debug information helps a lot in identifying the bugs in the design aspects and help us fix it. So for example, here we can see the sensor input corresponding to IC road has been determined, but it was the wrong data. So we could evaluate various aspects, including the functional and safety aspect of things. So these were the input data that was given to the system model. So we could see the sensor data file. So we have a lot of sensors defined in the model. So for each of the sensors, what was the traffic sizes, the packet sizes, the period, the start times, the traffic periods, the classes of the packet, then the transport protocols, whether it is a TCP packet or UDP. Then we have the task mapping table where we can map each of the ECUs to a specific resource. So each of the sensor processing will be mapped to the corresponding mapped resource file. Then these are the list of statistics that is generated from the simulation model. Here we could see the per task stats. So for each of the tasks, we generate the statistics corresponding to them and is displayed. And this is per task, so this is very useful from the software or the perspective. So we could be able to see how much each task consumes. Then here we have hardware stats, hardware networking stats, where each of the switch stats is being displayed out. We can determine what is the maximum buffer occupancy, the total bytes transferred across the ports, the minimum, maximum, and mean latency, the throughput consumed during the simulation. Now we go over to the failure analysis for improved safety and reliability. So we'll be looking at 5 different aspects: the hardware aspect, software aspect, RTOS, power, and network. So under hardware aspect, we will be looking at 4 different cases. One is when one of the processor core dies. So then we need to remap the task to active cores. So this will tell us whether our current setup of resources or the current number of cores are sufficient enough to make it achieve required performance requirement values. Then reducing buffer size due to memory loss, then the data due to electromagnetic interference, and sudden occurrence of alarms, which leads to more activity. So the last case, which is a bursty kind of test case. So suddenly there is a huge amount of traffic going through the network, and which will this kind of analysis will let us know how much can the network handle. And under the software test case, we will look at deadlock and Livelock test cases, resource starvation examples. And for RTOS, we will look at when the slot has been run over, which means we need to disable some of the slots so that the time critical applications run without any issue. So then we will look at the power, where we look at thermal shocks and life cycle loss in processor core shutdown. And at network failure, we will look at a fault injector and a brute force attack methodology. So under hardware, we could see the parameter list. So in the model, the user can evaluate the impact of each failure by using this checkbox. So let's say we want to evaluate a core failure, then we simply have to enable it, then run the simulation. So with and without failure, these were the results that we were able to obtain. So we could see that when the core one got failed, we could see the activity graph. Here in this graph, there is no continuation here. That is because the corresponding core was failed. And compared to here, we could see there is no continuity here. And the memory usage, we could see there's a lot of spikes happening, which is caused due to the corruption of data. And then due to the sudden activation of alarm, there is an increased workload accesses to processor cores. So that again affects and causes spikes in the latency. Now we look at the software failure. So this is a typical read and write problem where we read the old data while an updated data has been written to the memory. So these test cases can help us evaluate the criticality and the mismatches that can happen in the real environment. Because if we calculate the algorithm results based on an older data, then it can significantly affect the system's performance as well as the safety. So here we could see the incorrect packets, and here we could see the correct packets being read out. Now we look at another type of software failure, that is a resource starvation. So with sufficient amount of resources, we could see that the buffer occupancy stays at only 1. So there is only 1 packet at most all times. But with resource starvation, we could see almost all the resources are being hogged by task 3 and 2, and which leads to spikes. Not spikes, it keeps on increasing. The buffer occupancy, it keeps on increasing over time until it gets saturated. Now we look at the detection and handling of deadlock, the task graphs. So over on the left, we have no deadlock, which means that we could see the plots are being generated over time. The latency plots look considerably good. Even though there is a little bit of spikes, every task get completed. But with deadlock, we could see that the flow 0 is no longer being completed. So this means that the applications are no longer being able to execute, and which results in a critical failure. Now we look at the detection and handling of Livelocks. So here we are running the software code on the hardware, and we could see that the instructions are being executed in a loop. So these can be identified with the help of the debug messages that are being displayed. while the simulation. Now we look at RTOS failure. We could see that so here we are looking at the RTOS failure. The task there we have 3 tasks which are running on 3 different slots, and we must make sure that each of the tasks which is being run on the RTOS stays within the allocated time slot. If it doesn't, then it will go outside of the slot, which will cause the consecutive task to be shifted. So if it happens for consecutively, then the corresponding slot has to be disabled. So we could see that during the course of simulation, there was a lot of disabled slots. So these are all risks that needs to be evaluated very much ahead in design. Now we are looking at the core shutdown due to low power availability. So we could see the graph that has been captured when running without the power drop and with the power drop. So without the power drop, we could see that the latency can be seen, to be a little bit higher for the corresponding task, because here they were a little bit lower without the power drop. And over here we have the network fault injector. We have a table where the user can select various network failures that they want to inject into the model. Some of them include loss of communication via the message corruption, unacceptable delay insertion, message loss, message insertion, and so on and so on. So injecting a failure is very easy. They just have to add the network failure module into the model and then select and activate the corresponding failure that you want to inject. And these are some of the results that can be captured while without injecting and with injecting some of the network failures. So we could see without failure, the latencies are pretty consistent, but with message loss injected, we could see a significant spike in the latency. And here with incorrect addressing, we could see that even though the latency is not that high compared to the message loss case, but there is significant spikes happening over time. So evaluating all of these cases will and preparing for such situations will make our automotive E system much more fault tolerant and fail safe. So I would like to take it and show you some of glimpses into the future. So what we are currently working on and building towards is to the sleep and wake up protocol, that is the TC10, and on to the integrated software approach. So in TC10, what we are currently building here, a little bit more information on that is shown here. So for example, what happens in the protocol is that, let's say we have 3 switches, switch 1, switch 2, and switch 3, and they are all having a certain set of nodes connected to them. So for example, let's say the node from node 5, the node 5 want to communicate to node 2. So then it must send the wake up signals over the data paths. So it has to send the wake up signals. So there are timing requirements that needs to be maintained. So these are some of the work that is being under progress, and also the integrated software where we can enable multiple services per hardware, and the software is what actually defines the hardware. So based on the software requirements, we will have to update the hardware configurations. So this will be available and added to the tool in the next release. Now, a little bit information on Mirabilis design and VisualSim Architect. We are an engineering solutions focused on innovations in electronics. We are based in Silicon Valley, USA. We have various development and support centers across US, India, Japan, China, and Czech Republic. And some of the milestones that has been achieved by Mirabilis design over the years has been shown here. So over the course of years, we have won various awards and recognition in various conferences and shows. And we were in 2022, we were awarded the best show in embedded world. and we are currently preparing for the communication system designer in 2023. So the VisualSim and little bit more information on to the VisualSim Architect and what it is capable of. So it can do the analysis at a stochastic level or with the help of scripting languages, then look at algorithms, protocols, you look at the performance evaluations, power evaluations, the functional side of things. And with all of these being provided in a single platform, the user can evaluate the dependencies between them, the benefits of power management, what can it, does the power management has an effect on performance, what happens to the safety level, the quality of CPP code that needs to be incorporated. All of these can be evaluated under a single platform. These are the list of IPs that are available for the user to be reused into their design. So it ranges over from traffic generators over to the various processing units and network components, the time sensitive protocols, the switches, gateways, all are being supported in the library. So they can just drag and drop into the design. And here we are seeing some of the system modeling benefits that can be achieved when using the VisualSim modeling architect. So without using the VisualSim architect modeling technology, it takes a lot of time just for the model creation, then the analysis, and then the fine tuning or refinement. But with the closed loop approach and along with the AI enhanced diagnostic modules, we can save at least 30% of the resource time that has been allocated. So with this, I would like to wrap up today's webinar session. Please feel free to ask any questions in the chat window, and I'll be glad to answer them all. Thank you all.